Hi, my name is Brian Hoffman. I'm an employee at Siemens Energy in Orlando, Florida, and I'm also a distance education student at NC State University. I'll be talking about my experimental demonstration project for MAE 535. The topic is electromagnetic theory for concentric coil metal detectors. The underlying principle behind this type of metal detector is Faraday's law, and this can be expressed as, from our text, time-varying magnetic fields in the form of, say, electric alternating current and a stationary coil will induce electric currents in stationary conductors, such as a metal object in the ground. Mathematically, this is V induced is equal to the change in flux linkage, and which can also be expressed as magnetic flux times the number of turns. Basic operation can be demonstrated by the following video. First, you have alternating current in your transmitter coil, which is the outermost coil. This fluctuating magnetic field in this will produce eddy currents, and those currents will generate fluctuating magnetic fields, which will also be picked up by the innermost coil, and that voltage can be read off after it is set up the shaft. I've explained that here in 3 steps. Again, the AC current produces fluctuating magnetic fields, which produce eddy currents in the object in the ground. The eddy currents also produce fluctuating magnetic fields, which produce a current in the pickup coil, and then that voltage is read off. So for my metal detector lab setup, it's a very bare bones experiment. I've used a transmitter coil, which is a large red coil here, larger diameter, a receiver coil, which is the green, smaller diameter coil in the middle. I've also used an AC source in the form of a function generator for one of the local labs. And then I've used a digital multimeter to read the voltage off of the pickup coil. And finally, for my targets, I used a set of steel pliers and an aluminum U-clamp that I found around the lab. For my parameters, my transmitter coil was about 16 turns at a diameter of about 5.5 inches. My pickup coil was about twice the number of turns and half the diameter. For my function generator, I was applying 10 volts peak to peak at a frequency of about 50 kilohertz. And mathematically, again, you can see that your magnetic flux is related to your V, which is your I over 2 times the radius of the transmitter coil, times the number of turns of the transmitter coil, times the permeability of free space, times the area of the pickup coil. And then once you have your magnetic flux, you can use that to find your V induced. This is my laboratory setup of a basic metal detector. You can see I'm using a function generator there to generate a signal of 50 kilohertz at 10 volts peak to peak. I'm running this through my transmitter coil, which is the outermost coil here. This is also known as search coil. With a digital multimeter, I'm reading the pickup coil, which is the innermost green one here. And right now you can see that I'm getting a reading of about 850 millivolts from being in the vicinity of the transmitter coil. And what I'm going to do is I'm going to introduce a couple objects into the vicinity here, and what we should see is a change in the voltage reading on the multimeter from the eddy currents being generated inside of those 2 components. So the first one I'm going to use is a set of steel pliers, and then after that I'm going to use this aluminum U-clamp that I found here around the lab. So when I introduce the pliers, you can see the reading changes to about 820 or so millivolts. And then when I use the U-clamp, what I'm seeing is about 833 millivolts. So not only can this detector sense when a metal object is in the area, but by reading the change in voltage, you can actually tell what type of metal you're seeing.